Whenever data is transmitted, there are two separate questions to answer, and keeping them separate is the first thing to get right, because exam questions routinely ask about both, and students conflate them. The first question is about direction. Which way can the data travel, and can both ends send at the same time? The second question is about the wires. How many of them are there, and how are the bits spread across them? Those two questions are completely independent. A connection can be serial and simplex, or serial and full-duplex, or parallel and half-duplex. Choosing an answer to one tells you nothing about the other. So let us take direction first, then come back to the wires. There are three directional modes. Simplex means data travels in one direction only and it can never go the other way. A broadcast to a television or the signal from a sensor to a processor, the receiver has no way to reply on that connection at all. Half-duplex means data can travel in both directions, but only one direction at a time. A walkie-talkie is the classic example. You can speak or you can listen, and you have to stop doing one to do the other. Full-duplex means both directions at once, genuinely simultaneously, like a telephone call where both people can talk over each other. The distinction students most often get wrong is between simplex and half-duplex. Ask yourself whether the other end can ever reply on this connection. If it can, but not while you are sending, that is half-duplex. If it truly never can, that is simplex. Now the wires. Serial transmission sends bits one after another down a single wire in order. Watch what that means in practice. Here is a byte waiting to be sent, and a single line to the receiver. The first bit sets off, then the second follows behind it, then the third. They form a queue, each one following the last, and they arrive in exactly the order they were sent. Because there is only one wire, the bits cannot possibly overtake one another, and the order is preserved no matter how far they travel. That single fact is what makes serial reliable over distance. The trade-off is obvious from watching it. With only one wire, moving 8 bits takes 8 times as long as moving one. Parallel transmission uses several wires side by side and sends one bit down each of them simultaneously. Here is the same byte on 8 wires. Every bit sets off at the same instant. They travel together, and in an ideal world, they all arrive at the same moment, so the whole byte crosses in the time serial took to move a single bit. That is the appeal, and it is a real one. For a given clock speed, parallel is roughly 8 times faster over the same distance. This is why parallel connections are used inside a computer, between the processor and memory, where the distance is a few centimeters. So why is parallel not used everywhere? Because that ideal world does not exist. No two wires are electrically identical. Tiny differences in length, resistance, and interference mean the bits do not travel at exactly the same speed. Over a few centimeters, that difference is far too small to matter. Over a longer distance, it accumulates. Watch the same 8 bits again, but now with the wires behaving realistically. They still leave together, but some are already falling behind. By the middle of the journey, the byte has visibly spread out, and when they arrive, they no longer arrive together at all. The receiver is trying to read a byte whose bits turned up at different moments. This is called skew, and the result is corrupted data. That is why parallel is confined to short distances inside a machine, and why every long-distance connection you use, USB, Ethernet, a network cable, is serial. So the comparison comes down to this. Serial is slower for a given clock speed, but reliable over any distance, needs only one wire, so the cable is cheaper and thinner, and suffers no skew. Parallel is faster over short distances, but needs many wires, making the cable bulkier and more expensive, and is vulnerable to skew and to interference between adjacent wires, known as crosstalk. When a question asks you to choose, the deciding factor is almost always distance. Inside the computer, over centimeters, parallel. Between devices or across a network, serial. And note that modern serial connections have become so fast that they beat parallel even at short range, which is why parallel ports have disappeared from computers entirely. USB is worth knowing specifically because the syllabus names it and because the letters give the answer away once you notice Universal Serial Bus. It is a serial connection, half-duplex in its older versions, and it carries several practical advantages. The connector only fits one way round, so it cannot be inserted incorrectly. It is a universal standard, so the same port serves a keyboard, a camera, or a storage device. It supplies power as well as data, which is why a phone charges from it. It is automatically detected, so the operating system loads the right driver without the user configuring anything. And it supports several transmission rates, so slow and fast devices share the same port. The one limitation worth remembering is the maximum cable length, which is a few meters. Beyond that, the signal degrades. 3 things to take away. First, keep direction and wires separate. A question asking for the transmission method usually wants both. For example, serial half-duplex. So give both rather than half an answer. Second, if you are asked why serial is used over long distances, the mark is for skew and you should name it. Bits on separate wires arrive at different times and the data is corrupted. Saying only that serial is more reliable is too vague to credit. Third, when comparing, argue in terms of the actual trade-off, speed against distance and cost, rather than declaring one method simply better. Parallel genuinely is faster, it is just unusable beyond a short run, and that is the point being tested.